So, exam 6 is going to cover chapter 8 on bonding, general concepts. And I'm going to take the review document. I think this is version 1. There are a couple of versions of the review document. I'm going to use version 1. Version 2 is similar problems, just the names are changed to protect the innocent. So if you can do all the problems in one of the documents or the other, you should be fine on the exam. But I'm going to use version 1 and share it right now. There we go. Okay. That's probably big enough for everybody to see. And I got actually quite a few of these marked off that I think are important. So I'll just, I'm going to do the whole first page. So we'll start with number 1. After I check off another attendee. Okay. We might get one more. Let's continue. Number 1. Oh, before I start, does anybody have any specific problems that we need to deal with before I get into this? And if something comes to mind while we're in the middle, just interrupt me and we'll deal with your problem and come back to my selections afterwards. If not, we'll move on with number 1. The force between two bodies having identical electric charges. What does that mean? Well, it can either be negative or positive, right? So if one of them is positive and the other one's positive, what should you expect? You should expect that they should repel each other. Also, two negative charges will repel one another. What about negative positive? Well, just the opposite. They'll attract one another. So to answer this question, we just look for the one which the force between two bodies having identical electric charges is a force of repulsion. Pure and simple. That's it. No qualifiers needed. In fact, the qualifiers that are in the rest of the choices are wrong. So you have a choice, you have a force of repulsion between two like charges. All right, where do we see that in molecules? Well, positive ion, negative ion will attract. So you get the ionic bonding. Slight positive and slight negative will also attract. And if they're like charges, they will repel. They don't have to be full charges to repel or attract. They just need to be either opposite or like charges. Okay, number 2. Atoms having equal or nearly equal electronegativities are expected to form what type of bond? It looks like we have selections here. So if their electronegativities are very close to one another, what type of bond? If they're very far apart, then you would expect to have ionic bonding. If they're close together, they don't have to be exactly the same, but if they're close together, then you should have covalent bond. Then you want to look at how far apart are they. They're not far enough apart to be ionic, but they're not close enough to be nonpolar. So in that case, they would be polar. If they're very close together, they would be nonpolar. Okay, and we have rules to go by. What's the difference in electronegativities that would give you polar versus nonpolar, ionic versus covalent, and I'm not sure if those are listed in useful information or not. I don't think they are. We had them on their slides. Yeah, we had them in the review document, PowerPoints. So to answer this question, if their electronegativities are nearly equal, you should expect nonpolar covalent bonds. Right here. All right, I better start marking these off or I'll come back and try to do them over again. 3. The elements cesium, fluorine, and chlorine. For the elements cesium, fluorine, and chlorine, the order of increasing electronegativity is what? Well, what's the trend? The periodic trend for increasing electronegativity is lower left to upper right. So we've got cesium, fluorine, chlorine, correct? So I'm going to go down to periodic table. Here we go. Right. Where's cesium? You got to know where these things are. You can't use the trends, right? Cesium's down here in the lower left-hand corner. So what does that mean? That means it is the lowest electronegativity. So cesium is the least. Then you go to the other side to find fluorine and chlorine, right? They're over here. There's chlorine, there's fluorine. So chlorine is going to be less than fluorine. In a group, the lower ones are below. So the next one would be chlorine, followed by fluorine is the greatest. Now, did I put those in the right order? That's the question. Let me go back up. In order of increasing electronegativity, right? So that would be cesium, chlorine, fluorine, B. All right. I have to check this every now and then, be sure it's centered. All right. Number 4. The electron pair in the CF bond could be considered what? Well, let's see. We're talking about the 2 electrons that are there, right? That is represented by, like that. That electron pair in the bond could be considered what? Well, let's see what our choices are. Closer to carbon, because carbon has a larger radius and thus exerts greater control over the shared electron pair. I don't think so. What are we actually looking for? Right? It looks to me like they're looking for polarity of the bond. Which one is going to pull strongest on the electron pair? So let's look at B and see if that's where they're headed. Closer to fluorine. That pair will be closer to fluorine because fluorine has a higher electronegativity than carbon. That's it. Right there. That satisfies. And since there are no other choices here that say one of the above, 2 of the above, none of the above, whatever, then once you find it, you're done. It won't be closer to carbon, it won't be closer to carbon here. Inadequate model? No. The bond doesn't have to be ionic. Centrally located directly between carbon and fluorine. Well, that's not true, because we know that carbon is far to the left. It's 1, 2, 3, 3 positions left of fluorine. So it's going to have a smaller electronegativity. Fluorine is going to have the larger one and tend to pull electron density closer to itself. So that means B is the answer for number 4. All right. For number 5. Which of the following molecules has no dipole moment? Right. So what 2 things do we need to know to assess the polarity? That's what they're saying. A dipole moment means polarity. Which one of these does not have a dipole moment? You need to know 2 things. The polarity of the bonds in the molecule and the geometry. Okay, so let's look at them one at a time. CO2, let's see, ammonia, water, and then we have all or none. Okay, so what this tells me right here is all or none means we've got to look at each one of them, right? In case there are 2 or more that do have dipoles, or all of them maybe don't have dipoles. Has no dipole, that's what we're looking for. So let's look at, how do you tell? First, you have to draw the Lewis dot structure. So we say carbon and oxygen. Carbon has 4 electrons, valence electrons. So we have 4, and oxygen has 6. So that's 12. 16. All right, so you put the carbon in the middle and connect them with a single bond to start with. So that's 2, 4, minus 4, 12. So there's 6. There's 6. We're done. We're done placing electrons. Now we need to what? We need to try to establish an octet for each one. Both the oxygens have octets, right? We start from the outside and work our way in. Carbon does not. So can we get an octet for carbon without sacrificing oxygen? Yeah. Just make a double bond. Like that. Okay. So are those bonds polar? Well, yeah. They'll be toward oxygen, away from carbon. So that tells you what? That tells you the first condition you need. You have polar bonds. How about geometry? What do we need to know for geometry? We need the VSEPR model, which means you need to know how many groups surround the carbon. In this case, we only have 2, right? So what does that mean? 2 groups means linear molecule, right? Now we can put it all together. We've got polar bonds, but they're directly opposite one another, pulling in exactly the same strength. The magnitude is the same. So they cancel one another out. That means carbon dioxide is nonpolar. Okay? So if the rest of them are polar, then A is the answer. Okay, so let's make room for the others. How about ammonia? Well, you got like that. Well, let's count up the valence electrons first. Nitrogen is 5, and then plus 3 is 8 total. 8 electrons, 8 valence electrons. So we got nitrogen. Let's move it out here a little bit. And we've got our hydrogens. So 2, 4, 6. Hydrogens can't take any more electrons, so we have to go to the next inner, which is nitrogen. Okay? So all the hydrogens have their duets. Nitrogen has its octet. Right? So we've drawn the Lewis dot structure. Now we need polarity of the bonds. Right? They're going to be toward nitrogen. What's the shape of the molecule? Well, remember, you need the electronic geometry first. 1, 2, 3, 4. 4 electron groups means tetrahedron. So you've got a hydrogen back here, you got a hydrogen here, and a lone pair up there. Okay, so now, well, you also have, we can't say anything about the electrons yet. We only talk about dipole moments and polarities at this point relative to bonds. So what's your geometry now? Well, cover up the electrons and you have a trigonal pyramid. Which means what? Which means the dipoles are pointing like this, up like that. So add them all together and they're going to be that direction. So ammonia is a polar molecule. All right, we found one polar. Water's the third one. We've done water so many times, we might as well just draw it. So the dipole moment here is going to be like that. Okay? Now we know that there's only one nonpolar molecule. So that means that's out, that's out. There's your answer. 5 is A. All right. That's page 1. Let me see, page 2. Yep, we're going to do everything on page 2 also. Which of these has the smallest radius? Okay, let's put them up here because I want to go to the periodic table. So we'll get them up here. 6. We've got potassium ion, chloride ion, rubidium ion, sulfide, and argon. Okay. Now let's go to the periodic table. We're looking for the smallest radius. Let me write that over here. Smallest radius. Okay. Now we can go to the periodic table at the end because we're going to need to look at it. Rather than hold this one up in front of the camera, I thought this might work a little better. Let's see, there we go. All right, let me get this stuff out of the way so I can see too. Okay, where are these located? Well, let's see, there's potassium right there. Back up one and you get argon. Back up another one, you get chlorine and sulfur. And the only oddball in there is rubidium, right here. Okay. Now, if these were just neutral atoms, it would be a simple matter, right? What do we know about the radius of a neutral atom, the periodic trend, right? It's not in this chapter, it was in a previous chapter, actually. If you go from lower left to upper right, the atoms get smaller, right? So if you go up in a group, they get smaller. You go down in a group, they get bigger. If you go left, from left to right in a period, they get smaller, generally speaking. The transition metals tend to weave around a couple of places. But in general, as long as you're talking about the representative elements, left to right is smaller because you got more protons. Okay. So let's try to find the biggest one. How about that? Notice that sulfur and chlorine are to the left of argon. So sulfur should be getting bigger than chlorine. And if you add electrons, then it should be bigger than chlorine. And chlorine adds an electron. One second. If you add an electron, then actually sulfur 2- and chlorine 1- are isoelectronic with argon. And argon has more protons than chlorine, which has more protons than sulfur. So if this had the same number of electrons, but each one to the right has more protons, that means we're shrinking the ion. So the largest ion should be this one right here. This is the largest one. I'll put it over here. We're actually going to put them in order. Why not? And then chlorine's next. And then argon's next. So what would be the next one? Well, if you go to potassium, then you're adding a proton, but you're subtracting an electron, so it's even smaller. It's got fewer electrons than argon, but it's got more protons, right? So we would expect, well, if we're in the same period, we would expect an increasing size, but we're not. We're in a different period. We're actually down below argon, which means the next energy level out. But we've removed that one electron in potassium's valence shell, and we've still got an extra proton. So potassium should be smaller than argon. So what does that leave? Well, there's only one left. Rubidium. The problem is rubidium is supposed to be larger than potassium. Right? Go down, you get larger. So these should be reversed. Like that. Or if we put them in order, this one ought to be rubidium and this one ought to be potassium. Like that. Okay, so let's go back to the smallest one should be potassium. That's what we're looking for. Smallest radius should be potassium. So let's go back and see if I logically assess this correctly. Let's see, go back up, back up. Here we go. Yep, there's potassium. So at least I agree with the key. But that's the logic behind it. Oop, here we go. That was number 6. So if I'd ask you for the largest ion, it would have been sulfide. Okay, 6, 7. Which of the following arrangements in order of decreasing size? Okay, so now we do get, to do a size arrangement. 7. Okay, what are the possibilities? Well, let's see, what do we have here? Does each one have gallium in it? Yep. Each one have calcium in it? Yes. Potassium, potassium's in every one. Chloride, 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 yep. Sulfide, sulfide, yep. Okay, so we need to order gallium, 3+, calcium, 2+, potassium, chloride, and sulfide. Okay, we need to put those in order of decreasing size. So the biggest one will be first, right? We've already looked at these two right here. We know that this one is the largest one and this one's the next largest. So we're going to have this one is bigger than that one. Now we need to take the cations and put them in order. Well, let's go back and look at our periodic table to see where they are relative to one another. We know that if you subtract an electron from a neutral atom, it gets smaller. If you add an electron, it gets bigger. Here we go. Okay. So now we've got potassium, calcium, gallium. There's potassium, there's calcium, gallium. All three of them are in the same period. And what we know is that if they were neutral atoms, the gallium would be smaller than calcium, which was smaller than potassium. If you subtract electrons from them, right? 3 from gallium makes it tiny. This one's the next largest, and that was larger. Right? And simply because of the extra protons minus electrons. So the smallest one is going to be gallium. Then the next one is going to be calcium. And then the next one will be potassium. So they should be in that order. Let's go back. Here we go. So that looks like B. B is the correct order for size. All right. Let's see, there we go. Mark that one off. Let's do number 8. In a reaction between magnesium and sulfur, the magnesium atoms what? Become anions, cations, become polyatomic, share electrons with sulfur, crystallize. I think the last one who just ran out of possibilities and just threw something in there. Okay, so what happens in a reaction between magnesium and sulfur? Now, we assume that these are neutral atoms. All right, so this is number 8. So you have magnesium, metal, and sulfur. And for simplicity's sake, we're just going to say it's a single atom. We know that it could take other allotropic forms like S4 and S8 are common, but we're gonna say this. So what happens? Well, which one's more electronegative, and how far apart are they? All right, if we go back down to our periodic table, we find that magnesium is way over here. It's a metal. Alkaline earth. Sulfur is way over here. It's a nonmetal. So you can assume from the start that there is an ionic bond formed, metal, nonmetal. So which one loses and which one gains it? Metals always lose. So this one loses electrons. It wants to lose 2. Why would it want to lose 2? Because if it loses 2, it looks like neon, right? It has 12. And if it loses 2 electrons, then it looks like neon, which is a perfect octet. Those 2 electrons now transfer to sulfur. And now sulfur had started with 16. Now it has 18, and it looks like argon. Electronically speaking, of course. So magnesium becomes a positive ion. So let's go back and look at the question, be sure I answered it. Number 8. Okay, very close. There we go. So magnesium atoms become cations, just like that, which is B. All right, 9. Choose the molecule with the strongest bond. All right, this can throw you. Right? This one is somewhat counterintuitive. We have to consider 2 things in the strength of a bond. Okay. Let's put our choices up here first. Right. All are equal. Okay. Iodine here. Bromine there. Yep. Chlorine here. Fluorine there. Difluoride. Okay. These are going to be covalent bonds. They're going to overlap orbitals and share electrons. Right. So they all have that in common. The strength of the bond depends on 2 things. What's the distance between the atoms? The closer they are, the stronger the bond. Right? So you have bond distance. And the second thing you have to consider is, well, we did discuss strength of bond in terms of how many electrons are shared. Number of electrons shared. Right. And then we looked at, I don't know if we discussed this in class or not, but it's an important factor, and I'm going to introduce it here if we didn't talk about it, is potential repulsions. Okay, what do I mean by that? Well, we've already discussed the possibility of 2 positives repelling, 2 negatives repelling. How significant is that? And when we talk about, particularly in this case, electrons repelling, we're interested in electron density. So the smaller the space that the electrons occupy, the more intense their charge. Okay, even though you have the same number of electrons, if they're spread out, then they don't have the same intensity of charge and the potential repulsive force against other electrons. Okay, so what do we have here? How about the bond distance? Right? The bond distance decreases as you go up. So you would expect, based on that only, that difluorine would have the strongest bond. Now, why is that possible? Because these atoms are big and they get smaller as you go up, right? So they can get closer together. But look at what also is happening. Fluorine and fluorine, like that. And you can do the same thing for chlorine and bromine and iodine. You can draw this Lewis dot structure where you have these lone pair electrons out there. Okay, so what does that mean? Well, it means that those electrons are repelling you of one another. Right? The closer you get, the stronger the repulsion. Also, you're bringing protons closer together from the nuclei. But the nuclei are pretty much, well, they're not constant because you get more protons here and here and here. But they tend to be shielded. For the bigger atoms, those protons tend to be shielded. So you're really not changing much in terms of the effective nuclear charge as you go down. But what you are changing as you go down, we'll use this one as an example. What's the charge density for those electrons? These are small atoms. These are bigger atoms. The charge density around those chlorines is more diffuse than around the fluorine. So you get repulsive forces here that are stronger than they are for chlorine. Right? And then when you get to bromines, they're even more diffuse. Not only that, but the atoms are much, much bigger. So the bond distance is increasing. Okay? So what happens is that as you get closer together, the charge density increases, but it's not yet offset. It's not strong enough to offset the bond strength as the atoms are able to get closer together and the overlap is stronger. Then what you get is bond strength. Let's see, bond strength increases here and then decreases as you go up. So that's kind of counterintuitive until you examine the reasons for it. And we know that's true because we've measured the bond strengths and find that chlorine is the strongest. Dichlorine is the strongest bond of this whole family. So we just have to explain why that is. So this is sort of reverse logic. We would expect fluorine to be the strongest, but in fact, it's weaker than chlorine. Chlorine is the strongest because it hits the happy medium of bond distance, shared electrons, and potential repulsions. So that's why the answer here is B. All right. Here we go. That was 9. Let's look at 10. Oh, wait a minute. I marked the wrong one. Okay, the same choices. Well, let's see, does 10 have something to do with 9? Which of the following molecules exhibits the greatest bond energy? All right, that's another way of expressing strength of a bond, the bond energy. All right, so we did answer 10 also. More bond energy means a stronger bond. So what does that mean in practical terms? It means in order to measure the bond energy, you have to put enough energy into it to break the bond. And that can be measured. And that's how you know the bond is stronger. So 9 and 10 are really flip side of the same coin. All right, so we can move on to, let's see, are we going to do 11? Yep, we're going to do 11 also. So we have 11 and 12 are based upon these series: boron trihydride, nitrogen dioxide, sulfur hexafluoride, ozone, and phosphorus pentachloride. So draw the Lewis structures and then answer the following questions. So 11 wants to know which of the molecules obeys the octet rule. Okay, and the second one, based on the same Lewis dot structures, which ones have a 0 net dipole? Okay, so we can answer 11 and 12 by drawing the structures for each one of these. So 11, 12 can both be answered as long as we draw the structures for each one of them. Okay, boron trihydride. All right, we did that one in class, but it's worth repeating. So boron has how many valence electrons? 3. And 3, 1 each for hydrogen, so that's 6. 6 electrons. So we have boron, have hydrogen, 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 2, 4, 6, it's done. And there's no way to get an octet out of those because there are no extra electrons that can be placed around boron. Right, so this one does not obey the octet rule. Okay, how about, what's the next one? NO2. Okay, nitrogen has 5 electrons, oxygen has 6 each, so that's 12. 12 and 5 is 17. Right, so we have nitrogen, we have 2 oxygens. Right, so that's 2, 4. That means we have 15 electrons left. That's 12, so we have 3 electrons. Pair and an unpaired one. That unpaired one is known as a free radical. And then we want to let's see, we have 2, 4, 6, 7. So how are we going to get an octet for nitrogen? Well, if you make a double bond on either side, you're exceeding the octet. If you leave it alone, you're less than the octet. Right? So does nitrogen have the ability to accept more electrons? No. Nitrogen is in the second period. It only has S's and P's, orbitals. It has no access to d orbitals. That comes with period 3. So this is the way it has to be written. You can't add any more to nitrogen. There's no room for them. So this is the structure for nitrogen, and it does not obey the octet rule. Right? So no octet there, no octet there. How about 3? SF6. Right? Sulfur is 6 electrons, and fluorine is 7 times 6 is 42. So 42 and 6 is 48. Okay, so we have sulfur 1, 2, 3, 4, 5, 6 fluorines. Two, 4, 6, 8, 10, 12. So we got 12 electrons used up. So that means we have 36 left. So where are we going to put them? Well, we start from the outside. We can put 6 around each one of those. Right, 6 times 6 is 36. So if we do that, around each one, we've used them all up. So do we have an octet rule obeyed here? No. 2, 4, 6, 8, 10, 12. We got 12 around sulfur. Is that valid? Yeah, sulfur's in the third period. It has access to 3D orbitals. So it's real and it fits our model, but it's not, it doesn't obey the octet rule, right? So none of these obey the octet so far. How about ozone? Right? So oxygen has 6 valence electrons times 3 is 18. And we're going to have this, 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 and this. 2, 4. So that means we have 14 left over. 1, 2, 3, 4, 5, 6, 7, 8. Let's see, 2, 4, 6, 8, 10, 12. So that means we have 2 electrons left over. They go here. Okay. Can we make an octet for this oxygen here? Yeah. You just take these 2 right here, move them over there. So we have a double bond on that side. We could also have a double bond on the other side if we use the other oxygen, which means we're set up for resonance. But this obeys the octet rule all the way through. So that one obeys the octet. And the last one we got PCl5. PCl5. Okay, chlorine is halogen. That means it has 7 valence electrons times 5 is 35. Phosphorus has 5 of its own, so that's 40 electrons. So we have phosphorus, 1, 2, 3, 4, 5. Chlorines. 2, 4, 6, 8, 10. Means we have 30 left. 6 times 5 is 30, all used up. So we have 2, 4, 6, 8, 10 around phosphorus. That one doesn't obey the octet either. 4 is the only one that obeys the octet. Right here. Okay? So we answered 11. How about this one? These molecules have a 0 net dipole moment. So which ones, right? We have several to select from. Which one has a 0 dipole moment? Now we have to look at bond polarity and geometry. Okay. Boron should be slightly more electronegative than hydrogen. It's probably not much. But what's its geometry? Trigonal planar. They're all oriented equally around a triangle, which means they cancel one another out. This is nonpolar. Okay, how about this one? Well, you have 1, 2, 3, actually 4. That's tetrahedron. Nitrogen and oxygen are slightly different in electronegativities, but they're not much. Right? They're not much. But they do have a difference, and that adds up. So if you put these in a tetrahedron, then you look at the geometry of the molecule, it's bent. Which means any electronegativity, any dipole moment that is part of the bond will be additive. Bent, it's like water. Bent molecule, they add together. So this one is polar, although very slightly polar. How about this one? 1, 2, 3, 4, 5, 6. What is 6 groups? Octahedron. Right? That's also the shape. Right? So even though the dipole is toward the fluorines, they're all equally distant from one another. And they cancel one another out. So this one is nonpolar also. So there's one. There's one. How about this one? Well, this one's going to have 1, 2, 3 groups, which means trigonal planar. But we cover up that one lone pair, and you have a bent molecule. This one is polar. Oh, excuse me. Where's my mistake? They're all the same, right? They're all the same atoms. You got no polar bonds in there at all. So it doesn't matter what the shape is. They're all nonpolar. Okay? How about this one, PCl5? It has 5 and no lone pairs, so both the electronic and the molecular geometry are going to be the same. So 5 groups in these bonds means trigonal bipyramid. They're all equally spaced. They cancel one another out, which means they're nonpolar. Okay, so we should have this one, this one, this one, and this one. 1, 3, 4, and 5. 1, 3, 4. Why did I put 6 in there? There's no 6. That's a mistake. That should be a 5. I'm going to correct that right now. Let's see. Why did we put 6? Well, that's wrong. Why does it say only 1, 3, and 4? 1, 3, and 4. Oh. Huge mistake. I've got 1, 2, 3, 4, 5. See, 2, 4, 6, 8, 10. No, that's not a mistake. We got 10 here, and then we have 2, 4, 6 times 5 is 30. So PCl5 should also be nonpolar. Yeah. 1, 3, 4, and 5. 1, 3, 4, and 5. So that's the wrong answer. Right? This one should be D. This one should be D. 0 net dipole moment. Based on what we learned here, that's the right answer. Okay. All right. That was 11 and 12, 13. All right. How many electrons must be shown as bonding or non-bonding electrons in the Lewis structure whose skeleton is this? All right. That's not as hard as it looks. I'll show you why in just a second. Okay, let's get this situated. There we go. All right. So 13, we're looking at this skeleton. Carbon, 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 4 of them right there. Yeah. Then we have an oxygen here hydrogen there, hydrogen here, and then 3 here. All right. Those numbers here, they don't mean that you have that many carbons. Normally the subscript would mean that's how many you have. But in this case, they're just labels. So this one is labeled as 1, 2, 3, 4. Probably should have put a circle around them, right? So they wouldn't be confused with subscripts on number of atoms. So what do we know about this molecule? Well, you could go write the Lewis dot structure based on the atoms that are here. 1, 2, 3, 4. 4 times 4 is 16. Right? We have an oxygen, which is 6. We have 1, 2, 3, 4, 5, 6 hydrogens. So we should have, let's see, 28 electrons. Okay, total. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We got 8 electrons that need to be placed. Start from the outside in. All the hydrogens have their duets, so we can't use hydrogen. So we start with oxygen first, and we say this oxygen has 2, 4, 6. Now, what we haven't said is, where does the other go? We have 2 more electrons that need to be placed. Well, if you put them here, then there's no way that you can get an octet for these. This one's got an octet already. This one's deficient, that one's deficient. This one's deficient, but it can get 2 electrons from that oxygen. Right? We can just do this, and it's fixed. And it only needs that bond, a double bond here. Right? So where is that other pair going to go? It needs to go on one of these, right? So then we can take that pair, and if we make a double bond here, that's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Now we have octets everywhere. How many electrons must be shown as bonding or non-bonding? Okay, I've gone a little beyond the question. The question just says, how many electrons do we have to place? We did that already, 28. Right there. That answers the question. All right. Let's see. If we were to do, I don't have 14 marked, but how many electrons are shared between carbons 2 and 3? How many electrons are shared between those two? 2 bonds, 2 electrons each, 4 electrons. Right? So 4 electrons are shared between C2 and C3. That's the only way that you can place the electrons and get octets for everybody and duets for hydrogen. All right, so let's see. Oh, we could answer 15 because we've already done these. The only molecule in there that has double bonds, we drew them early on, is carbon dioxide. In fact, it has a double bond on one side and a double bond on the other side of carbon. It has 2 double bonds. 16. I do want to work this one over. So let's go to 16. Let's see. Yeah, we're still good. All right. In the Lewis structure for ICl2-, how many lone pairs of electrons are around the central iodine atom? Okay. So let's take that one. ICl2-. Okay. How many electrons do we need to place? Iodine and chlorine both have 7. They're both halogens. So we have 3 times 7 is 21. Plus 1. There are actually 22 electrons that have to be placed. The central atom is going to be iodine. Then we have chlorine. 2, 4 is 18 electrons left over. So we have 2, 4, 6, 8, 10, 12. We have 6 electrons left over. Only place they can go is on iodine. So we have 2, 4, 6. Okay, so 16. How many lone pairs are there? Well, 1, 2, 3 lone pairs. Right there. Okay? That was 16. Let's jump to 19. All right, here. How many resonance structures can be drawn for the molecule O3? Okay, ozone. 19. All right, we drew that one earlier. Right? So it's 6, 18 total. We got 4 there, which means 14. So we have 6 there, 6 there, minus 12 is 2 here. Okay? So if we're going to draw an octet here, we've got to steal from one side or the other. So we could either come from this side or we could come from this side. What does that mean? That means you've got 2 possible valid equal Lewis dot structures. Right? So that the answer is 2. You have 2 possible structures. For that question, the answer is B. All right, that was 19. About 20. Which of the following types of molecules always has a dipole moment? Okay. A, linear molecules with 2 identical bonds. Those never have a dipole moment because the bonds are identical. Well, that could be interpreted. If they're linear molecules, both of the bonds are identical, but they're polar, then they're opposite one another and they cancel, right? So they could be polar or they could be nonpolar. But linear molecules with 2 identical bonds, they're always nonpolar. So they, A is false, right? It never has a dipole moment. Which one always has one? Tetrahedral molecules with 4 identical bonds equally spaced. Those cancel each other out also. So this is, maybe I should write it this way. These are always nonpolar. These are always nonpolar. How about C? Trigonal pyramid molecules. 3 identical bonds. Trigonal pyramid. How do you get a trigonal pyramid? The only way that you can get a trigonal pyramid, molecular geometry, is for the central atom to have 1 lone pair. If you have a tetrahedron like that, and your central molecule here, then you could have something back here. A trigonal pyramid would put this at the top, at the apex, and put these at the base of the pyramid, then this one has to be a lone pair. That one will always be polar, simply because of that lone pair. Makes this end of the molecule slightly negative, always. Okay, see, remember, trigonal pyramid is not a regular geometry for the electronic structure. It just doesn't exist. The trigonal pyramid, right, only occurs when you have a lone pair. So we could go ahead and do D. Trigonal planar molecules, 3 identical bonds, those all cancel themselves out every time. And then none has a dipole moment. So that's wrong. So the answer is C. To number 20. How about 21? Which set contains the atoms listed in order of increasing electronegativity? We should be able to knock this one out pretty easy. $21. Yeah, 21. All right. What do we have to choose from? Okay, so it's mixed up. All right. So we're going to have to look at each one, it looks like. Yeah, they're all mixed up. So, increasing electronegativity. So, fluorine, nitrogen, carbon, and silicon. Fluorine, nitrogen, carbon, silicon. Increasing electronegativity. B, phosphorus, nitrogen, oxygen, fluorine. C, nitrogen, oxygen, chlorine, fluorine. Nitrogen, oxygen, chlorine, fluorine. D, that was backwards. Okay, so we have to take into consideration the sign here. So if we put them in the same order here, then let's put fluorine over here. Right, so it'll be consistent. Oxygen, sulfur, and silicon. There we go. And then sulfur, oxygen, chlorine, fluorine. Oxygen, chlorine, fluorine. Okay, so let's go to our periodic table. Keep going, one more. There we go, let's scoot down there. All right, so let's see if we can eliminate these really quickly. Which one should be the farthest to the right, if it's there? Fluorine should have the greatest electronegativity if it's in the group. This one's in the group, and it's at the wrong end. Can't be. That one's okay, that one's okay, that one's okay. This one is on the wrong end also, right? So we've eliminated those two right off the bat. Now, fluorine's over here at the far right, that's okay. So let's look at this one and see if we can find any inconsistencies. Nitrogen is to the right of phosphorus in this one. Nitrogen is above phosphorus, that's fine. Then oxygen is to the right and fluorine is to the right. So this is a good candidate. In fact, I think that's the answer. But let's be sure. Oxygen greater than nitrogen? Yeah. Chlorine greater than? They're about equal, actually, and then fluorine. but chlorine is below these other two. So I think based on that, it's probably not the right order. How about this one? Silicon. Is sulfur more than silicon? Yeah. Is oxygen more than sulfur? No. Oh, yes, yes, it is. And fluorine. What was the question? They're in the right order, aren't they? You know what I think? I think the left-right carets are in the wrong place. Right? Because this one is greater than oxygen. This one's greater than sulfur. And this one is greater than silicon. So that one works also. Here's what I think has happened. And it's a mistake on my part, I'm sure. Let's go back to the question. Number 21. All right, there's 21. If we had placed these in the same, if this caret was the other direction for each one of these, then the only one that's right is B. So I think that's a mistake. Needs to be corrected. Okay. 22. Yep, 22. All right. Oops, too far. 22. Let's see, am I running out of time? Oh no, I got got another half hour. 22. Which choice has the bonds listed in the order of increasing bond energy? All right. So what do we generally need to consider? Difference in electronegativity and length of the bond. So if your atom is big, the bond can't be short. Okay. Increasing bond energy. HF, HCl. Oops, wrong direction. HBr. Okay. CO, CO, and CO. Difference is number of bonds. F2, Cl2, Br2, D, N2, CC bond and C2H4, the reason we wrote it this way in C2H4 is so that you have to figure out what type of bond it is. And I'll show you what it is in just a second. And the CC bond in C2H6 are all the same. Okay. So let's look at these in terms of what we already know. We know that this is the strongest bond of all the halogen diatomics, right? That's the strongest. It should be over here. So that can't be the correct order. How about this one? Same atoms. This one has a single, double, triple. That's correct. The bond energy increases as you increase the number of bonds. That one's correct. So actually we found it because the same, they can't all be the same. But let's look at the others just for fun. So what would be the, how about the bond energy here? Actually, the bond energy goes the other way. HF is a stronger bond than HCl and a stronger bond than HBr. So that was reversed. Should be the other way around. And this one, the dinitrogen is the strongest bond. Why? Dinitrogen is like this. This bond, this carbon bond here is like this. Right? Hydrogen here, 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 and here. It's a good thing I showed you that because you might not figure that one out. Unless you draw the Lewis dot structure, which you can do. This one is just a single bond with 6 hydrogens, right? So this one is reversed also. Single, double, triple. Right? Can't be the same. So the only one that's correct there is B. And that's not 21 that we're looking at, it's 22. This one. That one is correct out of all of those. Okay, 23. I got that one marked also. Let's see. Why did I put that one in there? In the gaseous phase, which of the following diatomic molecules would be the most polar? '23. So we've got cesium fluoride, cesium chloride, sodium chloride, sodium fluoride, and lithium fluoride. You know, this one is worded incorrectly. We don't speak of ionic bonds as polar or nonpolar. They're either ionic or they're not ionic. So that's really a bad question. Which of the following diatomics would be the most polar? Well, actually, they're nonpolar because they're all ionic. So we're going to have to interpret this and say, all right, which one has the greatest electronegativity difference between the cation and the anion? If that were the case, then we would say, all right, which ones are farthest apart? And you look at your periodic table. Let's go do that. All right, so you've got fluorine, chlorine over here. Let's see, that needs to slide over a little bit, doesn't it? There you go. Fluorine and chlorine, right? And then you look at the distance between them, right? Lithium fluoride is in the same period, right? So that'll be a fairly strong difference in electronegativities. It'll be more than sodium. Actually, sodium should be even stronger, right? So that's more electronegative. Sodium and chloride would not be. So we're still here with this. But cesium is way, way far away in the lower left-hand corner, right? So it can't be that one. It's got to be a tie between these. We've got to break the tie. So fluorine is more electronegative than chlorine. That means that's the greatest difference in electronegativities. 23. Yeah, I'll get there in a second. Here we go. So cesium and fluorine are the farthest apart in electronegativities. They would have, I wouldn't call it the most polar bond, I would say the most ionic bond. So that needs to be corrected also. 23. All right, we done that one. I think what I'm going to do now, I want to be sure and get this one in live. So I'm going to go to the very end and come back. The very end of the questions and come back. Here we go. All right. 53. All right. In spite of larger electronegativity differences between bonded atoms, beryllium is way far to the left of chlorine. So it's going to be should be ionic actually. But we're going to, for time being, we're going to draw the Lewis dot structure and compare it to sulfur dichloride, which is definitely a covalent molecule. But the question is, beryllium chloride has no dipole, while sulfur dichloride does. Why is that? Well, if we draw the two versus that one, right? What do you get? Well, beryllium is has 2 valence electrons. Chlorine, 2 of those have 14, so that's 16. So if we do this, oops, 2, 4, so I have 12 left. Right? Chlorine is more electronegative, but beryllium, they're opposite one another. It's a linear molecule, right? They're, beryllium, well, we could satisfy beryllium's octet, just do this. But it's still a linear molecule. So that's why it's nonpolar. It's linear. They cancel one another out. Whereas this one, sulfur is 6, and 2 times 7 is 14, so we have 20 electrons. 2 from that is 18. Right? 2, 4, 6, 8, 10, 12. Equals 6 electrons left. So we have 2, 4, 6. So that's a trigonal bipyramid, isn't it? 2, 4, see, 1, 2, 3, 4, 5. Trigonal bipyramid. No, that's not right. I did something wrong. 7, 14. Sulfur is 6. So that's 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I put too many. There we go. So now around that sulfur, we have 4 groups, which means tetrahedron, which means when we cover up those other 2, that means this molecule is like water. It's bent, which means the, like that, like that. So that's why sulfur dichloride has a dipole moment. It's bent with polar bonds. Okay, and there it is in red and gray, the explanation. This one, what I want to do is draw the Lewis dot structure And if you have something like this on an exam, you're going to have to attach a drawing or print out the exam and do it by hand. You could finish everything up to this point, right? You can fill in these, and then you can print that page and draw in the structure and then scan it or photograph it and attach it along with the rest of the exam. Then you'll have everything together if you see something like this on the exam. So what's the Lewis dot structure of ICl4? Cl4 minus, correct? So you have 5 times 7 is 35. You have 36 electrons. So iodine's in the middle. You have chlorines around. 2, 4, 6, 8, which is 28 electrons. So we have 6 around each one of these. Oops. So 6 times 4 is 24, which is 4 more. So you have 2 here, 2 there. Okay. So what type of electronic structure is that? You have 6 groups, that's an octahedron. And the lone pairs are at the 2 apexes of the octahedron. That's as far as you can get them separated. That means the molecular structure is square planar, because these 2 pairs are opposite one another, and these are all in the same plane at 90-degree angles. Right? So that's why we write it that way. Right? These are in the same plane with your lone pairs. Right? Draw your lone pairs there, and then you bracket it with this negative sign. If you miss that negative sign, it's wrong, because it does have a charge. Okay, that means the molecule is nonpolar and its geometry is square planar. All right, now we can go back in the 15 minutes remaining and pick up some of these others. Of course, I'm going to stay here until I'm done, but I just wanted to be sure and get those done live. So let me go back to, let's see, is that right? Yep. Go back to 25. Let's just do it this way. There we go. 25. Which of the following ionic compounds has the largest lattice energy? The lattice energy most favorable to a stable lattice. All right. We're not given any numbers, so we can't actually compare lattice energies. So what do we need to do? We need to use some generalities. Right? So the largest lattice energy would be for which one? Barium oxide, beryllium oxide, cesium iodide, sodium bromide, and barium sulfide. Okay. Let's review what's required to give you the greatest lattice energy in an ionic crystal. One is the number of charges, right? So 1, number of charges on the ions. Okay. 2, the distance between the ions, which also implies higher charge density. So the smaller the ion, the more dense the charge is. So the size of the ion, size of the ions makes a difference. Right? Those two. If you have larger charge and smaller ions, then you get a higher lattice energy. Right, so let's look at these. All right, barium is a 2+, sulfur is a 2-. So there they have the number of charges working for them. But look where barium is. Right. Well, rather than scroll, let me just use this. Let's see. There we go. Barium is way down here. It is a huge ion, and sulfur is pretty big itself. Right. So that cancels out their advantage in charge. The size of the ions is just way too big. Very diffuse charge. Okay, so the rest of them are, well, there's barium oxide also. That can't be. Barium's just way too big. It puts that oxygen, right? Puts that oxygen way far away. Okay, how about beryllium? Well, beryllium is a 2+ charge, and oxygen is 2-. So, you know, that's a pretty good candidate. They're small ions. Beryllium is very small, right? Beryllium is way up here. It's an extremely small ion. So with a 2+ charge, it's charge dense. And then it's in the same family as oxygen, which means that the oxygen atom is small with a 2- charge, which makes it bigger, of course. But the number of charges, along with the size of ions, tends to favor that one. Let's look at the others just to be sure. Cesium. Cesium is way down at the bottom of alkaline metals. It's way too big. And iodine is a huge ion too. Plus, they're only single charges. How about sodium bromide? Well, sodium is sort of toward the top, but it's bigger than beryllium, and it's only got 1 charge. Plus, bromine is in the middle of the halogens with a -1 charge. So that makes, they lose on charge and they lose on size. So this one should have the highest, the largest lattice energy, right? You would have to put more energy into this crystal than any of the others to break it apart. That's what lattice energy is. All right, that's 25. Let's see, 25, 26. The first electron affinity value for oxygen is fill in the blank, unfavorable or favorable. And the second electron affinity value is favorable and favorable. Okay. So 26. And we're talking about oxygen. Actually, we're talking about, that's not even in this chapter. That's just checking to see if you remember from the previous chapter on periodicity. Oxygen, electron affinity. How do we measure electron affinity? Oxygen, gas, plus an electron yields oxygen -1 gas. And what's the delta H? Right. As the electron falls from infinity down to the oxygen atom, it gives up energy, right? So the energy is going to leave. So it needs to be exothermic, right? The first one should be favorable, right? The first electron should be favorable, right? So we can look at C and D as potentials. A and B cannot be. It's not endothermic. Now, the second one is what? Well, look at what it's got to deal with. The second electron affinity takes this one and makes, this one. So what's its delta H going to be? Well, we might be tempted to say that it's also favorable because we know that 2 minus is the preferred charge on oxygen. The problem is this, you're trying to get this to approach a negative, right? They repel one another. So this one would be positive. Okay, unfavorable. So the second electron affinity is unfavorable. It's endothermic. Okay, why then does O2 minus form? Why is it the preferred? Add them both together. Their overall is negative, right? So this one is sufficiently exothermic that it can afford for this one to be slightly endothermic. And still the overall process is exothermic. Plus, when you add 2 electrons to oxygen, it looks like neon. And that makes it very happy. So D is the answer here. Favorable for the first one, unfavorable for the second one. And it's not part of the question, but overall, the process is favorable simply because of the difference here. All right, that was 26. 26? Yes. 27. Okay. We still have a little time, don't we? I was jumping the gun. 3:45. Yeah, okay. So we got 5 minutes. Okay, 27. All right. Using the following reactions data, calculate the energy of an HF bond. Okay. All right. So we've got these three. And what are we talking about here? We're talking about Hess's law. We can combine these. We just need to identify what is the reaction that expresses the energy of the HF bond. Right? So in order to determine the energy of the HF bond, we need how much energy do you have to put in, endothermic, do you have to put into the HF molecule to break it apart. Right? So this is our target, HF gas. Remember, everything needs to be gas, because if it's solid or liquid, then you have intramolecular forces that have to be overcome before you actually start working on the bond, on the intramolecular bond. So everything's gas, and it needs to go to this plus this. And that delta H should be positive. Okay, if it's not, then we probably made a mistake somewhere. Okay, how can we use these other three equations? Right. The first one, H2 plus F2 yields 2HF. If we flip it and divide by 2, right? So if we say the first one is now HF yields H2 and F2. H2 plus F2. Now, what is delta H here? Well, what happens to the sign if we invert it? Changes to positive, correct? And then what if we divide by 2, which we needed to do to get rid of that prefix, that coefficient? Right. So we need to change the sign, divide by 2. 542, positive 542, divided by 2 is 271. So this one is 271 kilojoules. Okay, so we got this one taken care of here. Now we need to put H and F on that side. How do we do that? Well, if we use the second one, as is, that puts 2 H's over here. We only need 1. Right? So if we take a half of that one, we get a half H2 gas yields H. Okay? So this one is, we can leave the sign the same as it is here, but we need to take half of it, right? Because we've only got 1 there and a half there. So 432 divided by 2 is 216. Right? And that one's positive, this one's positive. Okay? How about the third one? Well, now we need some fluorine. We only need 1 fluorine, but we got 2. So we do the same thing to it as we did to the one before it. Correct? Let's see. I'm not so sure I'm going to get where I want to be here. Did I leave one out? H2F2. Oh, my mistake. Right? It was 2HF yields H2F2. And we took a half of it in addition to flipping it. So now half of that is that one, half of that is that one, half of that is that one. Okay. So this value is going to be half of 154, which is 77. Now let's see. If we bring all these together, will it give us that one? Well, let's see. This one cancels over here. This one cancels over here. That one and that one are both represented up here. So we already got that one. Okay, so now all we have to do is add those 3 numbers together. And then 271. 564. 564 kilojoules. Which is E. Okay? I'd be less likely to make that type of mistake if I had a bigger board to work with. Then I could just lay everything out. I'm trying to compress everything into a small space, and that gets me in trouble. Okay, 28. Oops, there we go. As indicated by the Lewis structures, which of the following would probably not exist as a stable molecule? Aha. That's a good question. All right, so I'm out of time, official time. So if you can stay, fine. If you can't, I'll just keep recording. All right, let's see here. Be sure this is centered. There we go. 28. All right. Okay, so we've got these 5 molecules that we need to do Lewis dot structures for. We've got CH3OH. We've got CH2O. We've got CH3O. We've got C2H2. And we have C3H4. Okay. A thing about writing organic compounds. When you have a carbon followed by hydrogens, the convention is that those hydrogens belong to that carbon. Those hydrogens belong there, those there, these there, these there. Okay? I think that might be confusing. So if we follow those rules, then now we need to count up the valence electrons. We've got 6 and 4 is 10 plus 4 is 14. 6 and 4 is 10 plus 2 is 12. Let's see, this is 6 and 4 is 10, 13. This is 2 times 4 is 8, 9, 10. And this is 3 times 4 is 12, plus 4 is 16. Okay. Now we put this one here, there, there, there. This one has an oxygen, and there's a hydrogen. Okay, so that's 2, 4, 6, 8, 10. So now we have 4 electrons left. Where do you put them? Work from the outside in. Hydrogens are full. So we got, next one is oxygen. Plus carbon's already got its octet. So we got 4 electrons, put them here, 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 here. That looks pretty good, right? Everybody's got an octet or a duet. Right? So we can cross that one off. That one's fairly stable. How about this one? Carbon, 2 hydrogens, and an oxygen. So 2, 4, 6. That means we have 6 electrons left. So we have 1, 2, 3, 4, 5, 6. But carbon doesn't have an octet yet. So we pick these 2, put them over here to make a double bond, right? Octets are full. Now duets, octets, we're good. So that one's good, that one's good. How about this one? All right, carbon, 1, 2, 3 hydrogens, and an oxygen. So we have 2, 4, 6, 8. That leaves 5 electrons. Okay, 1, 2, 3, 4, 5. So we can take this one and make a double bond over here. But now we've got 2, 4, 6, only 7 around oxygen. That's not stable. So I would say this one is a good candidate for an unstable molecule. It may exist, but it's not stable. In fact, I think that does exist. But it's very reactive. And it's very reactive for one, if not many reasons. That free radical, that unpaired electron is extremely reactive. Okay, how about this one? So we have 10 electrons, carbon, carbon, hydrogen, hydrogen, 2, 4, 6. That means 4 electrons left over. So we have 2, 4. So what are we going to do for carbons? Well, what if we take this one in here and this one over here? Make a triple bond. 2, 4, 6, 8, 2, 4, 6, 8. We're good. In fact, that is acetylene. How about this one? Carbon, carbon, carbon. 4 hydrogens. Right? Why did we put the hydrogens on the outside? Because you work those the same way as the electrons, from the outside in. So we have 2, 4, 6, 8, 10, 12. That means 4 electrons left. Where do you put them? Well, you could put them here and here. Working from the outside in, right? 2, 4, 6, 8, 2, 4, 6, 8. This carbon only has 4 electrons. So we need to take that pair, put them here, and this one, put them there. So we have a double bond there and double bond there. So that's 2, 4, 6, 8, 2, 4, 6, 8. That's a stable molecule. So this one right here, C, is unstable. Right there. That one's unstable. All right, 28, 29. Okay. Using the following electronegativity values, so you don't even have to look them up. Select the following group, the molecule that, select from the following group the molecule that fits the given statement. The molecule contains a carbon atom with a trigonal planar geometry. All right, so we got to draw the structures to find the trigonal planar geometry, molecular geometry. All right. So 29. Oh, that was starting to crap out on me. Let me get a fresh one. I remember slinging it with a cap on now. I did it with a cap off one time and just everywhere. Let's get it started. It takes a while to get them going. All right, let's try it again. There we go. Okay. 29. The molecule contains a carbon atom with trigonal planar geometry. You know what? We don't even need those electronegativities. Really? The first one, CH3, CH3, CHO. Remember, the carbons belong, the hydrogens belong to the carbon. So we're going to have this, that, carbon, hydrogen, and oxygen. Right? How many valence electrons do you have? Well, 2 carbons is 8, plus 4 is 12, plus 6 is 18, right? 8 and 6 is 14, plus 4 is 18. Yeah, 18 electrons. Okay, 2, 4, 6, 8, 10, 12. So now we have 6 electrons left over. So we work our way in, there, 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 there. All done. Okay, this one has all the duets. 2, 4, 6, 8, 2, 4, 6. We don't need any more bonds over here. We need them on this side. So we take this one, put it there. That makes a double bond. Now, what is the geometry around that carbon atom? It's 4 groups. That's tetrahedral. That's not trigonal planar. How about this one? 1, 2, 3. Trigonal planar. And there are no lone pairs. So the molecular geometry is the same as the electronic geometry. So that one is trigonal planar. If you're in a hurry in an exam, you found your answer. We know carbon dioxide is linear. We know this one, the carbon, has to be tetrahedral. Right? I'll bet you $1 it's like that. That's tetrahedral, and the chlorine doesn't have a geometry. Because there's nothing, well, there's this one attached to it. It's linear molecular geometry. And this one, we did this one before. Didn't we? Oh, sorry. There we go. Right? That's tetrahedral also. Tetrahedral, tetrahedral, both of them. So the only one that has trigonal planar geometry in it is this one. And it's around that carbon. So 29 is A. Okay? 29. All right, so let's see. How about 34? Hold on a second. I got a cat screaming to get out. Come on. Come on. Let's go. Let's go. Everybody out? It's going out. No? Nobody else? All right. I'm back. And we're looking at 34. Okay. I think this one's the one I'm using. Yeah, 34. I need to put this one out of the way. I'll try to use it. Okay. Of the following, which molecule has the largest bond angle? Okay. So we've got ozone, we've got OF2, we've got HCN, and we've got H2O. More than one of the above have equal large bond angles. Okay, what's the bond angle here? Well, remember their structure for ozone. Right? Let's see, that's 18, 2, 4, 6, I need 12 more. There. That's 6. 2, 4, 6, 8, 10, 12. Okay. So what's the bond angle around that central atom? Well, it's going to be trigonal planar, right? So the bond angle is going to be 120 degrees. You see that? If we do like that, and we have this oxygen in the middle, and you have oxygen here and oxygen here, like that, then this angle is 120 because you have to have 120, 120, 120, makes 360. So that angle is 120. That's a pretty large angle. What beats 120? Linear. straight. If we can find a straight one, then it'll be linear, have a 180-degree angle. How about this one, OF2, right? Oxygen, fluorine, fluorine. We have 7 times 2 is 14 plus 6 is 20. Right? So we have 2, 4, which is 16 left over. That's 12, which means we have 4 left over. There, 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 there. That's a bent molecule. It's tetrahedral to start with, right? And then the angle between the 2 fluorines would be 109.5 or less. Less than 109.5. So this one still wins over that one. How about HCN? Let's see, down here. So we have 5 and 4 is 9, 10. 10 electrons, carbon in the middle, nitrogen, hydrogen. So that's 2, 4. We have 6 electrons left over. 2, 4, 6. So we got to take these 2 here and here and make triple bond. Now what do we got? We got a linear molecule, 180 degrees. And water, we know, is less than 109.5 because it's also a tetrahedron, a bent molecule with a tetrahedron electronic structure, which means 109.5 is your starting point, and it's compressed by those lone pairs. So it looks like HCN wins. It's 180 degrees. Okay, 34. How about 35? Which of the following molecules is non-polar overall? Okay, to do this one, you need to know the structure. And of course, you need to know, does it have polar bonds? All right, so we got 35, yeah, 35. All right. You got SF4. And you got SF2. And you got CCL4. And this is D. H2S. And E is OCl2. Okay. Sulfur's got 6. 4 times 7 is 28. 28 plus 6 is 34 electrons. Right. Let's do that first. Count up the electrons. So this 2 times 7 is 14 plus 6 is 20. This one is 4 times 7 is 28 plus 4 carbons is 32. Sulfur is 6 plus 2 is 8. Oxygen is 6 plus 2 times 7 is 14. 14, 6 is 20. Okay, now we can do our structures. We have sulfur, fluorine, 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 fluorine. All right, so we know this one has dipoles toward the fluorines, right? 2, 4, 6, 8. 8 from that is 26. If each of these fluorines has 6, that's 24. That means you have 2 electrons left. And they go right here. Okay? So that means, what's our structure? It's trigonal bipyramid. 1, 2, 3, 4, 5. Trigonal bipyramid, but what's the molecular structure? Well, all we need to do to answer the question is it polar or nonpolar? Well, it's unbalanced, right? It's unbalanced as a molecular structure, so yeah, this one has to be polar. right? That one has to be polar. It's probably a seesaw. This one is 1 sulfur, 2 fluorines, right? So that's 2, 4, which means 16. And then we have 12, which makes 4 left over. Right? So around the central atom, and these are polar also, that direction, that direction. But this is tetrahedral electronic, 1, 2, 3, 4, and it's bent. So that means this one is also polar. Bent molecule. How about this one? Carbon tetrachloride. I've shown you this one before. Carbon tetrachloride is tetrahedron. It's regular, but they all cancel each other out. This is non-polar. How about this one? Right, 2 there, 2, 4, means 4 electrons left over. Another bent molecule. How about this one? OCl2. Chlorine is more electronegative than oxygen. It's like that. But we have 2, 4, which means 16 left over. Right, so that's 12, it means 4 left over, but here and here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's another bent molecule. Polar. Bent. So this one is the only non-polar in the bunch. Carbon tetrachloride. That's why C is the answer. 36. Which of the following are linear? All right. 36, yes, 36. Let's see. Here we go. 36. And we're looking for the molecules that are non-linear. NO2 minus B. C2H2 C NH3 minus. Oh, no, that's wrong. It's not A, B, C, D. These are just the molecules. Then HCN, oops, HCN, CO2, and H2O2. Okay, how about this one? Nitrogen has 5 valence electrons. Oxygen has 6 times 2 is 12. 12 and 5 is 17. Plus 1 is 18. So we have nitrogen, oxygen, oxygen, 2, 4, which means 14. Right? So that's 12. So you have 2 left over. Goes here. Okay. This is bent. It's trigonal planar first. Well, let's see. We need 2, 4. We need a double bond here. But it's still 1, 2, 3 groups, which means trigonal planar electronic or bent. So that's nonlinear, correct? So this one is nonlinear, right? How about this one? C2H2, we did that one earlier. That's acetylene. It's like this. That's linear. How about this one? 3 nitrogens. So we have 3 times 5 is 15 plus 1 is 16. N. So that's 4, which means 12 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. We need, let's see. Is that right? 2, 4, 6, 8, 10, 12, 14, 16. But that one's only got 4. So we need to do this and this. Right? That one looks like it's linear. Right? Is that what we're looking for? 36? Nonlinear. So that was linear, that was linear. Neither one of those work. How about this one? HCN. That's HCN. You can draw it out, Lewis dot structure. That's it. That's linear. How about CO2? We've done that one before. That's linear. How about H2O2? Well, let's see. 2 times 6 is 12, plus 2 is 14. So we have oxygen, oxygen, hydrogen, hydrogen. Okay. And we have, let's see, that's 2, 4, 6. Means 8 electrons left. 2, 4, 6, 8. Okay. So around each one of these is tetrahedral. Or when you cover up the electrons, you've got bent. So it's bent here and bent there. So that's nonlinear. Right? So this is nonlinear. So we have NO2 minus and H2O2 are both nonlinear. Right there. There you go. 36 is C. How about 38? Let's see. That's good. All right. $38. All right. The molecular structure of BrF6 plus is, oh, okay. It's fairly simple. Br F6 plus. Okay, how many electrons? Well, they're both halogens, right? So you actually have 7 halogens. 7 times 7 is 49. Take away 1. So it's 48 electrons. So bromine is in the middle. 1, 2, 3, 4, 5, 6 fluorines. Two, 4, 6, 8, 10, 12. This is 6, 3, 36 electrons. So if we put 6 around each one of these, that gives an octet there, times 6 is 36. Right. So if we do it like that, and then we count up 6 groups around bromine is what? Octahedron. And there are no lone pairs. So this one is an octahedron. Molecular structure. Where is it? Oh, here it is. Octahedron. There you go, right there. Okay. 38. Let's see. 39. Let's see what 39 is. What type of structure does XeOF2? Xenon oxyfluoride. Okay, xenon is a noble gas that has 8 valence electrons. Right? 8, 6 here, 2 times 7 is 14. Right? So we have 28 valence electrons. So in this one, which one's in the middle? Well, that's a good guess. We usually put the noble gas in the middle when it makes compounds like this. And that's what we're going to do in this case. So we've got xenon in the middle, simply because xenon has, it's a 5th period element. It has lots of orbitals available. So we'll do that, and we'll have an oxygen, and we'll have a fluorine, and we'll have another fluorine, like that. So 2, 4, 6 means 22 electrons. So we can put like this, 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 that, 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 there, there, there. So that's 6, 18. 4 electrons left. 2 there and 2 there. So what does that give us? Electronic structure. 1, 2, 3, 4, 5. Trigonal bipyramid. So the trick is, where do the lone pairs go? Right? If you're going to put the lone pairs as far apart as you can from each other, then they would go here and here. The xenon goes in the middle, and 2 fluorines and an oxygen go around in the plane, and the lone pairs are here and here. So that means the structure would be trigonal planar. So D should be the answer with that logic. Okay. Now, why would we say T-shape? The only way it could be T-shape is if we have, and this is probably like that, and then the oxygen is up here, like that. In that case, when we cover up that one and this one, we get here, here, here. I like trigonal planar, which means I need to change the answer. I would expect this one to be D. I don't know how it got T-shaped in there, but D makes more sense to me. All right. You know what? I better save this. Let me move that out of the way. There we go. And let's save that. There. Okay, 39 was that one. 44. We're getting there. Almost done. 44. Select the correct molecular structure for SiH4. Oh, this one should be fairly simple. 44. SiH4. Silicon is in the carbon group. So it has 4 plus 4 is 8 electrons. So silicon with hydrogens, that's it. There's 8, 2, 4, 6, 8. And that is tetrahedral, electronic and molecular. Right? So that one was fairly simple. Silicon tetrahydride, or this is also known as silane. Which is derived from, if we have this one, that would be methane. So this one is silane after silicon. And this one is Me, methane, after carbon, which is also known as a methyl group. Okay, that was 44. Let's see if I've got anything left, or if that was it. 44. Oh no, I got a couple more pages, don't I? Yeah, a couple of pages, not too many. 48. Okay, 48. In the molecule Xenon Tetrafluoride, how many pairs of electrons surround xenon, and what's the molecular geometry? Right. This should be fairly simple. This one, like that. So, excuse me, 4. No, I was right the first time. I said tetrafluoride. That's what confused me. I confused myself. This is difluoride. Okay, so that's 14 plus 8 is 22. Okay, so we have xenon in the middle. We have fluorine here, fluorine there. And that's 2, 4. So 18 is left. So we can have 6 around each one of these. That gives us an octet. All right, so we put 2, 4, 6, 8, 10, 12. So that means 6 electrons left. Okay. So what's our electronic structure? Well, first of all, how many pairs of electrons? Get that? Pairs of electrons. 1, 2, 3, 4, 5. 5 pairs of electrons. Okay. So what's the electronic structure? It's trigonal bipyramid. So it would do like this. The most efficient way to place things around the xenon would be a fluorine up here and a fluorine down here. And then the pairs, lone pairs of electrons, right there. That's the most efficient way to position them. A balanced form. That means the molecular structure is linear, right? Goes right through here like this, 180 degrees. Bond angle. So C is the answer for that one. All right. So that was 48, 49. Choose the member of each set that best matches the label. Okay, so for these 3 sets, this one, and this one, we say, for the first one, which one's more metallic? 49. We've got beryllium and barium. All right, which one's more metallic? The lower the electronegativity, the more metallic, because one of the characteristics of metals is they give up electrons. And the more easily they give up electrons, the more metallic they are. So which one, beryllium or barium? They're in the same group. Barium's toward the bottom. It has the lower electronegativity. So barium is the more metallic. The more covalent. N2O gas versus MgO, solid. Which one's more covalent? The closer they are, well, actually, this one's easy. If you have a metal and a non-metal, it's ionic. If you have two nonmetals, it's covalent. N2O is both nonmetals. That's more covalent. Highest electronegativity of this group, OSBr. Okay? Which one is up and to the right of all the rest? I would say oxygen. Yeah. Oxygen is more electronegative. So barium, nitrous oxide, and oxygen. Barium, nitrous oxide, and oxygen. E is the answer to that one. $49.50. Use the bond energies given below to calculate the enthalpy change for the reaction. Okay, we know how to do this one. 50. What you need to know to answer this one is the structure of the molecules. So which one is it? The energy you put in minus the energy that comes out. Correct? Because all the bond energies are positive. So the enthalpy is the sum of the enthalpies for the reactants minus the sum of the enthalpies for the products. And the reason we do it that way is these positive values mean you put energy in, and that's what you have to do to reactants. Put energy in, break all the bonds. This one, those are positive values for the products. So, but you're going to get that energy back as the bonds form. So that's why you need the negative sign in front of them. And that's why they're in this order. Okay. So let's look at the reaction. HCN. So how is that written? HCN. Like that. Plus 2 hydrogens. 2 hydrogens like that. I'm doing it that way to show you the bonds. And this one is, I'm going to have to put it down here. This one is CH3 and NH2. Excuse me. Like that. Right? Do the Lewis dot structure and you'll find that that's true. Now this has an extra lone pair, right? But the bonds that we break are here. Actually, these are the bonds that we form, excuse me. So how about the bonds that we broke over here? How many of them are there? Well, there's 1 carbon hydrogen, which is 413. There's 1 carbon nitrogen, triple bond, which is 891. And then there are 2 hydrogen bonds, hydrogen, hydrogen, 432. So we have 2 times 432. That's this side right here. How about this side? Well, we have 3 carbon hydrogens, which is 413. We have 1 carbon nitrogen single bond, 305, right here. And we have 2 nitrogen hydrogen bonds, 391. 2 times 391. So we add these together, and then we add these together, and we subtract these from that. So I need a calculator to do this one. So 413 and 891 plus that. Then we have 2 times 432. Add that together. This is 2168. For this side. And that's in kilojoules per mole. This side we have 3 times 413. Okay. Then we add 305 to it. And then we add 391 times 2, and add that one. This one is 2326 minus 2326. Okay? So let's see, I just need to do that, and I get minus 158 kilojoules per mole. Minus 158 right there. Okay? That was 50. And I think the last 2. What are you doing in there? Good cat. That's right, you better get out. Come on. Here. Come on. Out you go. Come on. Come on, Mitzi. Out. Get out. All right. Sorry for the interruption. Kids will be kids, whether they're human or feline. All right, the last 2. 51. Okay, put this one up here. I think this one's going to take some room. To do 51, calculate the lattice energy for rubidium chloride from the following data. Okay, what is the lattice energy of rubidium fluoride? The lattice energy should look like this. Rubidium, let's see, rubidium is 1 charge plus fluorine yields rubidium fluoride solid. So the lattice energy is when you take the gaseous ions and they come together as the solid crystal. That's lattice energy. Now, wait a minute. Oh, I'm sorry, I'm looking at the wrong one. I'm looking at 52. Let's go ahead and do 52 since I got started. 52. We'll come back to 51. I'm already way over anyway. So the lattice energy for rubidium fluoride then is that right there. So can we deduce that, add things together so that we get the value from these things? Okay, we need to understand what these abbreviations mean. Okay, this one is fairly simple. Rubidium solid to rubidium gas. So what needs to happen? Well, normally what you would do is take rubidium as a solid and make a gas out of it. And then you would take the gas and ionize it. Okay? But that's backwards. That needs to be back over here, like this way. Okay, we'll deal with that in just a minute. Then for this one, you would need to take the fluorine gas, break it apart, right? Then you would take each one of those and you would electron affinity produce the ion. Okay. All right. So, let's see. This is called sublimation. Remember, solid to gas is sublimation. And then once you get it to this form, you want to produce this ion. Okay. Am I looking at the wrong way? Rubidium. Oh, chloride. I'm sorry. There we go. There we go. And there we go. Okay. Chloride. Fluoride. This is chloride. And there we go. Okay, so the values that we are given right there, where do they belong, right? This one is the first one, 85.8. This takes 85.8 kilojoules. Okay. This one is the ionization energy for rubidium. That's 397.5. kilojoules. That's the second one. BE. What is that? BE is bond energy. What is the bond energy of this chlorine? And that value is 226. And the next one is electron affinity. Oh, excuse me, I skipped one. Formation of rubidium chloride. I didn't do that one yet. Okay, I will do that one. Electron affinity is minus 332. Minus 332. kilojoules. And formation of rubidium chloride. Yeah, formation of rubidium chloride is in these terms. Remember, rubidium chloride is a solid, and you form it from its standard state elements. So this has to be a half. And that rubidium, this is a solid, that energy is minus 431. Minus 431 kilojoules. That's what each one of those means. Now what we have to do is arrange them in such a way that we can add them together and end up with that one. Right? So this gas, let's see, we need this one over here. Where is it? Here. So this one's going to have to be flipped. That puts the gas on this side. That means this one has to be flipped and put the gas on that side. This one is here. So that one goes the right direction. Oh, no, excuse me, it's on the wrong side. This one needs to be over here. And then since this chlorine gas is on that side, then this one has to be on the other side, but it needs to be half that size. All right? But that doesn't give us the rubidium chloride yet. This gives us the rubidium chloride. All right. So that's what each of these descriptions mean. Okay. Now we need to put them together. So I'm going to have to erase this and then put it back up there in the proper order. All right, so here we go. The sublimation. Well, actually, we're going to use the electron affinity. Let's see. Yep. So now we're going to have this one. And that energy is going to be minus 397.5. Minus 397.5. And these are all kilojoules. Right? So notice 397, we had to flip that ionization energy because that's what this is. This would be ionization energy going that direction. So we had to change that. This one is now 332 kilojoules. Right? It was negative 332 before. Electron affinity would be this direction, but we need it that direction. So now the sign changed. The next one, rubidium solid plus 1/2 chlorine gas. This is the energy of formation. Rubidium chloride solid gives us minus 431. Right. We didn't have to change that one at all. So if we're shooting for this one, let me put this back up here. Gas plus chlorine gas yields rubidium chloride solid. Okay, we've got this one on the right side. We've got this one on the correct side. That needs to be a gas, sorry. And we've got this one on the right side, right here. But we've introduced these terms that need to be gotten rid of. So that's what we're doing from here on in. So we're going to sublimate in reverse. Right? We had it going this way. Now we're going back the other way, and that's why the value is minus 85.8. Minus 85.8. Because it was positive 85.8 before. Now this one, we're going to need 1/2 of this one. So 1/2 of minus 226, bond energy. Bond energy would go back this way. But 1/2 of the sign change would be minus 113. Okay? So now let's see if we got rid of everything that we don't want. This is going to be 1 chlorine gas. There. How about this rubidium? There it is. Got it going. This is rubidium solid. Here. Okay? So that means this chlorine, this is 1/2 of a chlorine, and this is 1/2 of a chlorine, right? Half there means half there. There, there. So that one's out, 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 in, out, out. We're good. Now, if we add those together, we get this equation. Now we just need to add up the numbers. And it should be kilojoules per mole. Minus 695 kilojoules per mole. Right here. Okay? That took a lot of work, I'll have to admit. Now let's go back to 51, and that'll be the end of it. Last one for today. All right, 51. Okay, 51. Given the following information, each one of these, and actually this is similar to 52, except that we're not aiming for lattice energy, we're aiming for this, the enthalpy of this reaction right here. Okay? So that's our target reaction. I'm going to put it over here. 2 lithium solid plus 2 HBr gas yields H2 gas plus 2 lithium bromide solid. That's our target. How are we going to get that? Well, fortunately, we're given a lot of information here, and it's already built up for us. What we need is lithium solid on this left-hand side. Lithium solid, here it is. But how many do we need? We need 2 of them, don't we? So 2 lithium solid yields 2 lithium gas, and that value is going to be twice 166. Right? So we got 332 here. Okay, so we got this one taken care of. Right. Now, how about HBr? HBr would be, we need 2 HBr. Where's HBr here? There it is right there. Bond energy, HBr. So we're going to have HBr gas, 2 HBr gas, yields 2H gas plus 2Br gas. So where does that one come from? It comes from right here. Right? So we need to double 363 to 726. So now we got this one. Okay. How about hydrogen? Well, we need hydrogen on the right, right? Where do we have dihydrogen here, gas? Let's see, it's right there. It needs to be on the other side, right? So we put 2H on this side, and that leaves hydrogen gas on that side. But we doubled it, did we not? No, we just flipped it. We just flipped it. So it's minus 432. Okay, now we need lithium bromide on that side. 2 of them. Anybody have lithium bromide? Here it is right there. Okay. But we need 2 of them. And it's on the right side. So all we need to do is double it. So instead of 809, it's minus 1618. So we got this one. What's on this side? 2 lithium gas plus 2 bromine gas. Okay. Now, we've got all the ones we need. We got to get rid of some things. Well, this one's already done, right? That one cancels, right? So we need to get 2 lithiums on this side, 2 lithium ions on that side, and 2 lithium atoms on this side. So where is that coming from? Here's a lithium ion and here's a lithium gas, but they're on the wrong side. Are they? No, they're on the right side. So all we have to do is double it, right? We got 2 here and 2 here, so this one has to be doubled. So 2 lithium gas yields 2 lithium ions plus 2 electrons, right? And that's going to be double minus 809. Wait a minute, I'm looking at the wrong one. 520, excuse me. 520 doubled. So that'll be 1040. So that's plus 1040. Okay, that gets rid of this one there and this one here. So what do we got left? We've got bromine here and bromine ion there. So do we have that? Well, we got bromine on the left-hand side. It's on the right-hand side here. And bromine ion on the right-hand side is on the left-hand side here. But we need 2 of them. Right? So we need 2 bromine gas yields 2 bromine ion gas plus 2. Oops, sorry. Electrons on the wrong side. 2 electrons. Because the electrons have to cancel too. And the value for that bromine is minus twice this, minus 650. There we go. So now we got rid of that one there, and this bromine, that bromine there. So all of these are counted for, there, 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 and we got these in the proper proportion. So now all we have to do is add that list of numbers together. 332 plus 726 minus 432 minus 1618 plus 1040 minus 650. And I get minus 602 kilojoules. And there it is right there. Oops. There. Okay. I think that's it. It's enough, isn't it? My brain's fried. Okay. That's it for today. Any questions or comments?